Welcome to Lecture 4. In this first segment, we're going to go through a laundry list of laws of propositional logic. What these laws are really just a bunch of logical equivalences that are very important for you to know. For example, here is the first such logical equivalence. P or Q is logically equivalent to Q or P. Let's call this law or logical equivalence C1, since it is the first law of commutativity. Commutativity just means that the order of the operands of the disjunction does not matter. You can swap the order of P and Q all you want, you'll still get a logically equivalent proposition. There are at least a couple reasons why it should be pretty easy for you to understand and remember C1. First, the meaning of the logical equivalence is pretty intuitive. The second reason is that if you replace the logical or propositional variable P and Q with the integer variables x and y, and you replace the disjunction operator with the addition operator, what you get is an arithmetic expression that expresses the idea that x plus y is equal to y plus x. That is the same law of commutativity, but in the context of arithmetic, which says that the order in which you add two numbers does not change the result. Now notice the difference. Another difference between logic and arithmetic is that in logic, we're talking about logical equivalence, whereas in arithmetic, we have an equal sign. The values of x plus y and y plus x are literally equal. Of course, in the case of logical equivalence, it's the truth values that are also equal. So again, the symmetry or the analogy is pretty straightforward. Now let's erase this arithmetic expression, and let's consider a second law of commutativity, namely the one that applies to conjunction. And let's call it C2, which states that P and Q is logically equivalent to Q and P. Again, the intuition for why this logical equivalence is true should be pretty straightforward. But you can also remember this law by translating it again into arithmetic. And this time you replace the conjunction operator with the multiplication arithmetic operator to get the well-known commutativity law of multiplication, namely x times y equals y times x. Again, let's erase this arithmetic expression, since what we really care about here are the laws of propositional logic. The third law that you need to be comfortable with is the first of the De Morgan's laws, DM1, which states that the negation of a conjunction is a disjunction of the negations. The intuition for this logical equivalence is the following. If it's true, or if it is the case that P and Q are not true at the same time, not P and Q, then it must be the case that either P is false or Q is false. That's the first such law. And the second one is symmetrical by swapping the and or connectives. And it says that the negation of a disjunction is logically equivalent to the conjunction of two negations. So the intuition here is, if it's not the case that at least one of P or Q is true, then it must be the case that both P is false and Q is false. The next law is, again, pretty intuitive. It says that P or P is logically equivalent to P. We call this the first law of idempotence. And what it states is that it doesn't matter how many times the same operand appears in a disjunction. You can always remove the redundant ones and just keep one of them. Indeed, if P is true, then clearly P or P is true, and if P is false, then clearly P or P is false. And the same holds for conjunction, which gives us the second law of idempotence. P and P is logically equivalent to P. The next law is one that we discussed a couple times already, so I'll go really fast. It's called double negation, and it simply states that not P is logically equivalent to P. In other words, you can always eliminate the double negations in any proposition. Next comes the first law of associativity, which states that if you have a proposition that contains two or more disjunctions, like here, it doesn't matter the order in which you compute the truth values of the disjunctions. In other words, you can associate the last two operands together or the first two operands together, and you will get the same truth value. That's called associativity. This should look very familiar to you, since when we switch to the arithmetic domain, and in particular we place disjunction with addition again, we see the very common rule that the order in which you perform additions does not change the final result. So let's keep the logical law, and let's look at the second law of associativity, which is identical except that it applies to conjunction. Again, it does not matter the order in which you compute the truth values of the operands. You can associate from the right or from the left, you'll get the same truth value. In arithmetic, this translates into the associativity of multiplication, which is also well known to you. The next two laws are probably the only ones that might take you a little bit more effort to memorize. The first one, D1, is the first law of distributivity. And what it says is that disjunction distributes over conjunction. In other words, P or Q and R is logically equivalent to P or Q and P or R. Now, when we build the analogous arithmetic equation, something strange happens. So let's replace the variables and the operators in the usual way, and what we get is actually something that is not an equation. In other words, in arithmetic, addition does not distribute over multiplication. So you can't carry from one domain to the other. It does not hold in arithmetic, but it does hold in logic, so watch out. Now it turns out, as you can imagine, there's a second law of distributivity called D2 that is obtained from D1 by swapping the disjunctions and conjunctions. And what it says is that not only does disjunction distribute over conjunction, but the reverse is also true. In other words, conjunction distributes over disjunction. So when we convert this second law of distributivity to arithmetic, we get something that actually is true in arithmetic, namely multiplication does distribute over addition. This equation here is definitely always true in arithmetic, and it is also true in logic. Now let's wrap up this laundry list by considering 4 more logical equivalences that are short and intuitive. The first one, called DO1, is the first law of domination. And what it says is that P or true is logically equivalent to true. In other words, whatever the truth value of P, true dominates, since the overall value of this proposition is always true regardless of P. Now, what is that T, by the way? T is not a propositional variable. Actually, it's the logical constant true. Or another way to think about it is T basically stands for any proposition that's always true, namely a tautology. So that's the first law of domination. Here is the second one, which is obtained by swapping disjunction and conjunction and swapping true and false. And what it says is that whatever the truth value of P, P and F of false is logically equivalent to false. In other words, false dominates P. I think you already knew these logical equivalences, but it's worth your while to write them down. And by the way, this one has an analog in arithmetic. If you replace the constant f with the arithmetic constant 0, you get the well-known equality x times 0 equals 0, whatever the value of x. Okay, now the last two logical equivalences are called identity laws. The first one states that P and true is logically equivalent to P. In other words, adding a conjunction with true never really helps, because what you get back is the original or first operand of the conjunction. Now the analog in arithmetic is obtained by replacing the constant t by 1, and again conjunction by multiplication. And of course, as you know, x times 1 is equal to x, whatever the value of x. That's the corresponding arithmetic equality. And finally, the second identity law states that P or false is always logically equivalent to the simpler proposition P. So, adding a disjunction with the constant false never really helps. You might as well just stick with whatever proposition you started with. By the way, what does F stand for? I forgot to mention that. Well, again, it's the logical constant false. Another way to look at it is you could always replace F with any proposition that's always false. Namely, you could always replace F with any contradiction. And this concludes our laundry list of propositional logic laws that you're responsible for knowing, understanding, and memorizing.